Hi. Hello in person. Hello Zoom. I'm Ginny Broadhurst. I'm the director of the Salish Sea Institute. And I'm going to start with a land acknowledgement because we're coming to you from Western Washington University's main campus, which is situated on the ancestral homelands of the Coast Salish peoples who have lived in the Salish Sea Basin throughout the San Juan Islands and the North Cascades watershed from time immemorial. We express our deepest respect and gratitude to our Indigenous neighbors for their enduring care and protection of our shared lands and waterways. So the Salish Sea Institute and Western Washington University Alumni Office welcome you to today's webinar. It is titled, as you can see, Climate Change in the Salish Sea Bioregion, Observed and Projected Trends in Temperature and Precipitation. And I'm really happy to be here with Dr. Aquila Flower. It's always a pleasure to hear her talk. Aquila is a broadly trained geographer with research interests in climatology, biogeography, and geographic information science, also known as GIS. Few people don't know what it actually stands for. She holds BA, MS, and PhD in geography, so she's nothing but consistently focused on geography.
I am loyal, yes.
Her research focuses on the role of climatic variability, human land use patterns, and natural disturbances in shaping forest, alpine, and coastal ecosystem dynamics, particularly in the Salish Sea region. She's very committed to the Salish Sea region. She is the director of the Spatial Institute and the primary faculty advisor for WWU's GIS degrees and climate change minor, which she was instrumental in creating. She teaches physical geography and geospatial technique courses. Aquila is also part of our Salish Sea Institute's Fellows Program, which helps to support and fund her research. So, with no, oh wait, I have a housekeeping item, sorry. Aquila is going to talk for about 45 minutes, so we'll aim for having time for questions at the end. Those of you on Zoom, you can use the Q&A function, which I think by now everyone is familiar how to do that. We recommend you use the speaker view as part of Zoom. And I will turn it over to Aquila.
Okay, thank you, Ginny, for the introduction and your ongoing support. Ginny is my patron saint of my research, I think, always supported me. Well, thank you, everyone who's here in person and online people who I can't see. Thank you also for registering. I'm delighted to be here today to report on some of the first results coming out of an ongoing project I'm working on, trying to create a comprehensive climate change assessment for our Salish Sea bioregion. So today I'm going to talk to you specifically about temperature and precipitation variables. There's all sorts of other stuff that's changing with climate change, and that will be at a later talk, at a later report. So these are the initial results. And I don't want to leave you hanging with any sort of like cliffhanger mystery. Yes, it has gotten warmer here. Okay, there's not going to be a plot twist. This chart here shows temperature averaged across our kind of long climate stations in the Salish Sea bioregion, going back to 1900 over here and up to 2022. And that red arrow shows that increasing trend. So that's what you would expect. But there are nuanced details in terms of variability across space and across seasons, differences with precipitation patterns, and then I'm going to try to tell this bigger story of beyond just, yes, it has on average gotten warmer. Cursor back. Okay, so well, Ginny said most of this stuff here, right? But let me just brag about my involvement with other Salish Sea Institute projects, and that I was the cartographer for the State of the Salish Sea report, and that I'm the author of the Salish Sea Atlas, which I'll talk about a little bit more later. And that has also been supported by the Salish Sea Institute. Salish Sea Fellow, yes. Okay. There's that beautiful photo from the State of the Salish Sea report. If you love Salish Sea things and you haven't looked at that, you should. You can download it online. All right, so we have, I think, a pretty broad audience, and I don't want to assume too much about background knowledge, so I have a few background slides, and sorry if you are a climate scientist, but just make sure we're talking about the same things when I say words. So first of all, what is climate change? Climate change is not an individual weather event, right? Climate change is a persistent, long-term change, a trend in climatic conditions. So we're talking over multiple decades, maybe over centuries. We're not talking about it's cold in January next month, and then we say, well, climate change isn't happening. Okay, we got to look for a consistent trend. We see for the world as a whole about 1.1 degrees Celsius or almost 2 degrees Fahrenheit of warming since 1850 to 1900. This figure, that number was coming from around 2020, so it's a little bit more by now. It's always inching up. All my figures are always out of date with climate change things because the change keeps happening. So it's a global phenomenon. This chart here, I didn't make this. This is showing global temperature anomalies, or the difference from the long-term average conditions, just showing that upward trend over time. Why is it happening? Okay, I actually teach a whole introduction to climate change class, and here it is in one slide. Because human activities that release greenhouse gases lead to more energy being stored, retained within Earth's climate system, instead of escaping to space. So we have this energy imbalance. We are keeping more energy than we're releasing. If our climate system was in balance, energy from the sun would come in, and it would eventually go back out to space, and there would be no long-term buildup or change in the amount of energy present within Earth's climate system. Instead, we're seeing this imbalance. And that means we're going to see warming in response to that because there's more energy to do that warming. The big culprits here, I don't think I have a little pointer thing. Carbon dioxide is the biggest one. This chart over here, I know it has all these technical terms and things on it, but really it's just saying bars to the right mean a thing that makes the world get warmer, and bars to the left, a thing that makes the world get cooler. Carbon dioxide is the big one. It has the biggest bar up there of all the greenhouse gases. It's the biggest by volume in Earth's atmosphere. Humans are adding a lot of it to the atmosphere. And it's of particular concern because it sticks around in the atmosphere for centuries, many centuries. So the decisions we make today about changes to how much carbon dioxide we're adding to Earth's atmosphere is going to affect future generations for 500 years or more. So that's why we hear a lot about carbon dioxide in particular. Where is this all coming from? This little chart over here from the EPA tries to show the breakdown. Electricity and heat production is about a quarter, responsible for about a quarter of greenhouse gas emissions. Agriculture, forestry, deforestation, and other land use practices like that are responsible for another quarter. And then we have industrial and transportation type impacts. So all these different components of our economy, right, they all have a carbon dioxide cost embedded within them because so many different sectors within our economy produce greenhouse gases. Okay, one more about where it's coming from. There's so many different ways to think about like who's responsible, which countries are adding the most greenhouse gases to Earth's atmosphere. I think the best way to look at it is by thinking about cumulative CO2 emissions, adding it up from the start of the Industrial Revolution and just keep going with that tally, because we know that carbon dioxide sticks around so long that things our ancestors did in the 1800s are still affecting climate today. So this chart just splits it down into some different groups, and I just want to point out Europe and the United States stand out ahead of the crowd in terms of their cumulative carbon dioxide emissions. This also shows just a sort of huge steep spike in world cumulative CO2 emissions. How big is that? Well, you've probably seen a figure like this before, looking at data from ice cores, where they can reconstruct carbon dioxide levels back hundreds of thousands of years. Notice there's that little dashed line. That was the highest it ever got for 800,000 years until now. And today, we are at over 420 parts per million. Just notice that's off the top of this chart. Again, this chart is already out of date. So we are outside of the natural range of variability that has happened during the entire time that humans have lived on Earth, have developed all of our economies and agricultural practices. This is a very unusual set of conditions in our atmosphere for our species in particular. And we're seeing the effects already. This is not a concern about something that's going to happen in the future only. It's already happening. Last year was the hottest year on record by a big margin. Just little news headlines there reporting on that. And notice this spike on the right here in this chart. This is showing global average temperature in each year. really high towards the right-hand side. In fact, the 10 warmest years on record in our historical record, when we've had climate stations recording temperature, all happened in the last decade. So it's not just like 23 was anomalous. For a feeling of how far out of the normal range we're at, I just want to show this figure. Every day in 2023 was at least a degree Celsius above the pre-industrial temperatures. So just consistently the whole year. So a big takeaway that I always try to share with my students is that we are not waiting for climate change to happen. We're not worrying about something that's going to happen later. We are already living in a climate-altered world. This chart here shows descending bars in blue there for years when the global average temperature was lower than the kind of long-term average over the 20th century. Red bars show years when it was above average, warmer than normal. Notice they're all red over here. So anyone you know who was born after 1976 has spent every year of their life in a climate-altered world where the temperatures are above the long-term average. Yeah. Oh, climate doesn't care about calendar years. I don't know. Yes. Thanks. Good question. I probably grabbed this in November when I didn't have the final data for that year. Okay, so here we are in this climate-altered world. And we've heard about this. We know it's probably affecting things here. So we might wonder, what is going on here in terms of climate change? Those charts I was just showing you were global temperature averages, right? 2023, warmest year on record, but it wasn't really extremely warm for us here in Bellingham compared to 2021. That was warmer for us. So there's variability in how these trends play out locally. So I have questions as a resident of this region. How has our climate changed since the start of the 20th century? And when we're thinking about changes into the future, if we're thinking about now as our starting point, as our baseline, we're missing the fact that we've already changed a lot compared to what ecosystems and cultural practices have been adapted to for a long time. Okay, and then, well, how is it projected to change over the 21st century? Yeah, it's going to get warmer, but what are the other details? Where can you get climate data for the region? Say you want to make your own map, or you just want to like look up some numbers. Where can you go and find a data set that tells you about this specific region? And this all adds up to wondering what this global phenomenon caused by global economic and technological trends, what does that look like in my own backyard? And I think literally of my own backyard a lot because I'm a gardener and I really see the differences year to year depending on what's happening with temperature and precipitation patterns. So if you want to answer these questions, and you haven't seen my talk yet, you would go to authoritative sources like the Intergovernmental Panel on Climate Change, the IPCC. That is where you should start. This is an international body of top scientists in both physical climate science and social science fields who bring together their expertise to write these assessment reports. That's wonderful, but it is focused on the whole globe. So you get results like this sort of chart up at the top there, global surface temperature change relative to 1850 to 1900. It has these little colored bars sort of indicating different potential scenarios, different pathways in the future. But the point I want to make here is that this is for the globe as a whole. This doesn't tell us exactly how much change we're going to see here. Same with sea level rise. Here we are on the Salish Sea. We were concerned with sea level rise. This chart shows global mean sea level change, but we know that there are local differences in places where, say, tectonic forces are causing the land to go up or subside. We're not really getting the picture of what's happening here by looking at that chart. The map on the right there from the IPCC shows darker red blobs where we've seen more warming, cool with less warming in blue. And I just want to show that there are these patterns across space, that we're not seeing the same amount of warming everywhere on Earth. That means we want to look at something local. So let's say you're wondering about how climate change is affecting your own backyard. You go to the IPCC, that gives you wonderful background information, but you don't know what's happening locally from these things. So you might go and look for some local sources. By the way, I am showing good sources, even though I'm saying that each one has something that isn't quite all of the things I need, right? This is from the Climate Impacts Group at the University of Washington. They have this really nice interface where you can go onto their website and look at projected changes for the future in precipitation and temperature variables. That's great. But notice, there we are in Bellingham, right up in that corner there. All of a sudden, the data go away. It doesn't continue into Canada. If you're thinking about changes to the Salish Sea, you're going to wonder about what's happening to the other half of our region, the other half of the sea. You're going to wonder maybe about what's happening with the Fraser River that provides over 60% of the fresh water to the Salish Sea. That's not included in this map, right? The Climate Impacts Group also has this website I really like with temperature trends observed at individual climate stations. So this isn't a projection of the future. This is an analysis of things that have already happened, how temperature has changed. I think this is great, but again, it stops at the border, and also it's separate from the future projection. So you kind of have to go back and forth in between those sources to think about past and future changes. Here's another source. You want some Canadian data. The Canadian Climate Atlas is wonderful. It has so much in-depth knowledge, so many different variables. I adore this, but notice the big gray blob that is the United States. Again, we've split our region in half. For those of us living in this transboundary region, we're always getting half of the story from those standard nation-based reports. So I'm frustrated by this. Therefore, I want to do this climate change assessment report that I'm working on, where I'm compiling, harmonizing, so I mean making them match up, analyzing and visualizing both historical climate records and future climate projections for our region specifically. And I'm creating a set of interactive maps to communicate these results. So you can go into a website and click around and get the details for an individual climate station or watershed. I also will eventually, when this is all done, compile and release data sets. So people who want to do analysis of climate patterns, make maps, look at the tables, they can just get a data set automatically, easily for the whole region, instead of going to a US website and then going to a Canadian website and downloading two data sets and trying to make them match. I show this slide a lot, so sorry if you've come to some of my other talks, but sometimes I say, well, I have got to do this work to harmonize these data sets from the two different sides of the border. And it sounds like, well, what's the big deal? Why is that so hard? And so this is my slide of complaints about why this is hard. So first of all, sometimes there's the data you need just don't exist. I'm running into that with sea surface temperature records for the Salish Sea region. We have nice long records in British Columbia. We don't have really nice long records in Washington. So sometimes you can't get past that. But maybe the data do exist, but they're housed by a lot of different agencies. This map here is just showing some of the larger jurisdictions in the Salish Sea to give you an idea of that jurisdictional complexity. So a lot of different organizations, government agencies, and so on that might have the data you need. And so if you want to make a cohesive analysis or map, you have to go to all these different sources. You have to be familiar with all these different sources. That really slows down research and communication, I think. Then you do get the data, but you'll find often that they don't line up in some way. They might not line up spatially. Their extent, their scale, their generalization, or just like where the boundaries are may not match up. Often I download a US and a Canadian spatial data set, and I'll find that the international borders sort of overlap, like implying there's some sort of contested boundary where there isn't. So it can be something as simple as that. It just takes some time to fix it. Temporally, it's another form of not matching up that often happens. The US and Canadian censuses happen 1 year apart. It drives me crazy. But often you're getting different time periods of data, and then you can't really compare them directly. And then the one that I spend the most time on is working with conceptual mismatches. When we're talking about small differences like units of measurement or type of data collection, or bigger things like the categories and scales that we use to record characteristics. Say you were looking at increases in heat waves. If you're using different thresholds in the different countries, you'll get different results that aren't directly comparable. In some of my other work, I've looked at, say, forest types and ecosystem types, and those are defined differently with different phrases that can't directly automatically be matched up across the border. So a lot of work goes into creating data for a transboundary region. I should have gotten a job somewhere within one country, not on the border, right? But no, it's an exciting challenge. So my bigger project addressing this sort of stuff is the Salish Sea Atlas, which is open access, all free, digital, interactive atlas online with maps, interactive maps, static maps you could print, designed to sort of communicate about our region. But I will go by that quickly. Just in case anyone is here for climate change and not for the Salish Sea, I'll just show you in pink what I mean by the Salish Sea here. Here's the official legal outline of the Salish Sea. It is a transboundary or multinational estuarine ecosystem. It is an estuary because there's so much fresh water mixing in with the salt water. So it has different characteristics than, say, the open Pacific Ocean. And just so you know, with very bold colors, it's made up primarily of these three large water bodies: Puget Sound, the Strait of Juan de Fuca, and the Strait of Georgia. Some people in Washington get confused and think it's just Puget Sound, but that's actually a small proportion of the total water area. And in my work, I'm interested about things that are happening on land where I live, not just in the ocean. So I use this definition of a bioregion, this bigger region that includes land around the sea that's not defined by political borders. It's instead, in the way I've defined it, it uses watershed boundaries as a natural delineation of the water, of the landscape. So this map here shows the 33 coastal watersheds that I include when I'm doing analysis of the Salish Sea region. And these watersheds are a great way to delineate regions because the freshwater moving through them comes into the Salish Sea. So we know there's this connection in between the land and the water in these areas. Okay, so on to climate change assessment. Now that we know where we're talking about, we know what we mean by climate change. Just some details about the data in case you're curious. One set of data that I used was from climate stations. So like these little guys here, right? That have been in place for over a century. I chose only stations that had at least a century of data available so that I could see long-term trends. Unfortunately, that meant I didn't get any stations from the northern part of the Salish Sea. I do have Canadian stations, but they're all in the kind of southern Canadian portion of the Salish Sea. This map here shows the 20 climate stations that I analyzed for temperature and precipitation patterns. And from these data sets, I could extract these tables like this that are ugly and not as good as a map. You'll see them look better eventually. And I looked at monthly minimum, maximum, and mean temperature, as well as total precipitation for this analysis. If you know these acronyms, the data are from the USHCN and AHCCD networks. These are both networks of high quality climate stations that have been adjusted statistically for when things happen, like moving the station location or like cutting down all the trees around the station and building impervious surfaces, which would create an artificial change in climate if you didn't adjust for it. So these are high quality stations. The station data gives you really detailed data month by month over the whole time period, but it doesn't cover the entire region. So I'm also looking at both historical and future data sets that are these interpolated statistical data sets. So they're using statistical techniques to estimate what the temperature or precipitation is in the areas in between the climate stations, based on climate station data, but extrapolated, interpolated out to a larger area. And for my future climate data, I use this form of interpolation along with something that's called statistical downscaling, which basically just means that you correct for elevation. Because global climate models, they give us climate projections, they create output over these really big grid cells. And so they're missing out on the nuances of an area like ours where we have big changes in elevation over kind of small areas. For the future analysis, I use what's called an ensemble, an average of 8 different global climate models that have been specifically ranked as doing a good job for our region in particular. And the biggest difference in between future climate projections that you might look at is not because of differences in the global climate models and how they create their physics-based mathematical models of climate. It's not because of that. It's because of differences in what we're now calling the shared socioeconomic pathways, SSPs, which basically just means a storyline about what greenhouse gas emissions will be like in the future based on changes in population, economy, and technology. So anyway, I used SSP 2-4.5, This is kind of a middle of the road, business as usual scenario. It's not the highest greenhouse emissions, and it's not one of those like really optimistic low emission scenarios. I'm going to focus on that. I'll show a little bit of analysis of how different things look with different scenarios. But just know when you're interpreting climate projections for the future, you always have to know what the assumptions are about greenhouse gas concentrations in the future. Okay, now let me actually show you some stuff. So here's that chart I showed at the beginning, looking at the difference from the long-term average each year going back to 1900, averaged across my climate stations. This analysis showed me that we've had an increase of 1.14 degrees Celsius, or about 2 degrees Fahrenheit, in between 1901 and 2020, averaged across the climate stations. This is looking at mean annual temperature. But let's look at how that varies in space, right? It's easy to look at a line chart and think, well, there's one big line, every station is responding consistently. That's not always the case, depending on the variable that you're looking at. So here's a map that shows the trends I found using simple linear regression models in temperature records, mean annual temperature records, at the 20 different stations that I analyzed. Red shows places that had an increase warming trend. There's no blue on this map, but for some other variables, we'll see some cooling trends. For mean annual temperature, it's a warming trend everywhere. The hollow circles show that it was not statistically significant. This trend was not statistically significant at the 95% confidence interval. Just ignore that if you don't want to hear about that. But just like we're a little less certain. It warmed, but a little less dramatically. So we are slightly less confident. But notice there's only one of those. It's at the station in Mount Rainier. All the other stations show a significant trend. And so we see this range of increases from 0.21 to 4.47 degrees Fahrenheit. And this is pointing out that there is some spatial variability. We're seeing warming across the region, but some stations, because of their local site conditions, have experienced more warming already than others. Now that was mean annual temperature for the whole year, right? There are also seasonal differences. This is a box and whisker style plot. If you're not familiar with them, we're basically just showing those long bars, showing kind of the range of the lowest and the highest values across all our climate stations. And the little line that goes through the middle of the box is showing our median. So think of that as our average value across stations. For mean annual temperature, in pink, you can see the annual data that I just showed on the map. And then I have winter in blue, spring, summer, and fall. Notice that there is an increase in all seasons. This blue line shows the 0 line. We're above that for our trend, so we're seeing warming in all the seasons. The biggest increase we see happening in summer, that red box there, as it goes up a little bit higher in the trend. So there's spatial variability and there's seasonal variability in how much warming we're seeing. What is that going to look like in the future? Here's mean annual temperature projected into the future. These are little screenshots I made of some of my web maps. Over here is our 1991 to 2020 kind of average temperature over that 30-year period. There's a legend down here, but purple is colder and yellow is warmer. And over here is the 2071 to 2100 map. There's a lot of detail in here. So I don't think you can really pick it out. Just notice that we're getting to those warmer hues. A lot of that brighter green and yellow color coming in. Averaged over the whole Salish Sea bioregion, these maps tell us that we have a projected increase by the end of the 21st century of over 4 degrees Fahrenheit in our mean annual temperature. Now, I think it's a little hard to pick out patterns in such a detailed map like this. So I did another analysis where I figured out the average change, projected change for each watershed in our region. And this map here is showing our 33 different watersheds. They all show warming. Yellow and orange is all warming. We see 2 to 2.4 degrees Celsius, or 3.6 to 4.3 degrees Fahrenheit of warming across all of the watersheds when we're looking at mean annual temperature. I'll show a version of this that's an interactive map later on where you can click around on the individual watersheds and look at these patterns over time. Okay, so that was mean annual temperature. Yes, it's getting warmer over the whole year. It's getting warmer in every season. But mean temperature is the average over the whole day and then average it over the month. So a lot of averaging. It really, what we experience often is not that average temperature. We experience the coldest part of the day, our minimum temperature. We experience the hottest part of the day, our maximum temperature. Those sort of bounding extremes are what matter most to us and to a lot of organisms, I think. So I want to look also at maximum and minimum temperatures. And I'm focusing here for maximum temperature on trends in the summer values of maximum temperature, because I think that's when maximum temperature is the most significant for, say, cooling your house costs or for negative effects on ecosystems that have their growing season and a lot of the life cycle happening during the summer. So this map, same style as the previous one, but now we're looking at observed trends at these 20 climate stations in summer maximum temperature. Interestingly, it's not as completely consistent and strong as we saw in mean temperature. And you'll see later that's because some of the increase in mean temperature came from changes in minimum temperature, not just maximum temperature. So for maximum temperature, we see increases at 17 of the 20 stations. Notice there's some hollow circles. They're not all significant trends. Average increase of 1.74 degrees Fahrenheit over that 1901 to 2022 time period. We also see seasonal variability once again with maximum temperature. That map I just showed you was looking at summer maximum temperature trends, but notice that winter in blue there is actually that median bar across the middle is actually the highest. Winter is the season with the highest increase in maximum temperature. I'm looking at summer because I think that's more biologically, economically meaningful to us, but it's not representing when we're actually seeing the biggest increase in maximum temperature. Still, we see this increase at most stations in all seasons. Right, that blue bar again is showing 0. Our boxes are above that. Future climate projections for maximum temperature. So we're seeing it warming across all seasons on average, though unequally different stations. When we look into the future, same sort of idea, looking at the historical map and the future projected map, where we're seeing more of those red colors, warmer conditions. We see for summer maximum temperature, a projected increase of over 6 degrees Fahrenheit, which is kind of a startling number to me. I have to double check these. That's a lot. And we see warming in every watershed, at least 2.8 degrees, okay, I'll do Fahrenheit, at least 5 degrees Fahrenheit. And for some of our northern watersheds, on average across that watershed, a warming of more than 8 degrees Fahrenheit. Okay, so that's maximum temperature. Takeaways there, biggest warming in the winter, biggest impacts in the summer, 6 degrees warming projected for the future. So we're seeing a lot of change in maximum temperature. What about minimum temperature? I'm pretty worried about, maximum temperature because like my garden gets too hot and my house gets too hot because it has a lot of windows and it's secretly a greenhouse. I'm also concerned with winter minimum temperature though. That's going to tell me for my backyard when my plants are going to stop growing for the winter, right? That's going to tell me when I need to make sure my kids put on gloves. Winter minimum temperature is personally meaningful to me every day when I'm getting dressed to go out. So what's happening with winter minimum temperature? Well, here, unlike maximum temperature, we see warming at every station except one, Port Angeles, which you can barely see, but it's a little blue circle over there. An average increase of over 2 degrees Fahrenheit in winter minimum temperature. So for a lot of stations, we're seeing a bigger change in minimum temperature than maximum temperature when we're looking at our historical data. Once again, minimum temperature increased in all seasons. There are 2 climate stations that mess this up by having a little decrease in fall, but generally, most stations show an increase across the seasons. The biggest average increase in minimum temperature is actually in the summer. So here I set up my analysis. Definitely I want to look at maximum temperature in the summer and minimum temperature in the winter. And then it just so happens for our region, and this is not true everywhere around the world, we're seeing a stronger trend in minimum temperature during the winter and a stronger trend in maximum temperature during the summer. Still, though, for both variables, we're seeing warming across all seasons. So here's some future projections. Winter minimum temperature. Takeaway here, we go from those cold purple icy colors, something that looks, I don't know, still like ice, but a little less cold over here. More of those bright kind of blue colors. We see across the region as a whole, a projected increase of 2.6 degrees Fahrenheit in winter minimum temperature, and maybe a bigger increase in summer temperature, which I don't have the number for up here. Again, looking at watersheds to see the spatial variability, we see some interesting trends with higher levels of warming in minimum temperature in the southern part of the Salish Sea, kind of the opposite of that pattern we saw with the maximum temperature map. Overall, we're looking at maybe up to almost 4 degrees Fahrenheit warming in winter minimum temperature for a given watershed. Though there is one watershed, Harrison, up in the north there, that had a tiny decrease just to mess up my results. And I'm going to look into more into why that is. I don't have an answer for that yet, but all the other watersheds do show projected warming for winter minimum temperature. Okay, that was a lot of charts. Big temperature story. Last variable I want to show you, not temperature, it's precipitation. In temperature, there were some interesting seasonal nuances, but generally we're just seeing most areas are getting warmer in all the seasons. Precipitation gives us a much more interesting set of mixed signals. This figure here shows, now I have 18 climate stations that had precipitation data. I was looking at 20 for temperature, but 2 of them, Canadian ones, didn't record precipitation. And this analysis for precipitation goes from 1901 to 2012, 10 years less than I had for temperature data because, again, some of the Canadian stations cut off earlier. Anyway, on this map, blue shows areas or climate stations with an increasing trend in total annual precipitation, which is add up all the rain over the year and snow. And red shows a decreasing trend, places that are getting drier. Again, a hollow circle is not significant, and a solid circle is significant. So this is a mixed bag when we look at these historical patterns. We're not seeing a consistent fingerprint of climate change on precipitation yet. We are seeing a bunch of changes, though. But the local topographic setting of these different climate stations is influencing how climate change plays out in the trends that we're seeing here. This points out how important it is to look at results for your individual local climate station, the nearest climate station, because averaging a bunch of negative and positive trends across the whole region gives the impression of less change than is actually happening, right? Because they're kind of canceling each other out. And yet I did that, and I will tell you that the number is 3.97 inches of increased total annual precipitation if you do average it. But I don't think that really tells the story of what's happening for my garden in the backyard. Okay, total annual precipitation has some patterns of seasonal variability, as we keep seeing. Interestingly, here's our 0 line. Winter, the average value is a decrease in precipitation that has been observed since the beginning of the 20th century. Though there are stations with an increase and there are stations with a decrease, but on average it's decreasing. Whereas all the other seasons on average have shown an increase in precipitation. And I'm going to hold that in our minds because we're going to see that that pattern does not continue into the future. Here's a future projection for just total annual precipitation. Now we've got a different legend, but red is drier, blue is wetter. I hope that's intuitive. Just looking at the patterns of change, it doesn't look as different between the historical time period and the future time period as when we're looking at precipitation, as when we're looking at temperature, but we do see changes. If you look into the Bellingham region, we're seeing some little expansion and contraction of some of those red areas. Overall, if we look at the whole region, for our climate projections, we see for the year as a whole, an average increase of what's equivalent to 7.8% more precipitation over the year as a whole. But let's look at that by watershed. So again, this is total annual precipitation. We see increases in almost all the watersheds. We see 3 watersheds around Puget Sound that are actually projected to see small decreases to total annual precipitation. And then we see these much bigger increases to the north. So there's this kind of gradient across latitude in terms of what's happening with precipitation, projected to happen with precipitation in the future. And again, that means you need to look at your local conditions if you're going to make plans for the future based on these data. Okay, this is total annual precipitation. Interestingly, though, summer precipitation shows a pretty different pattern, right? So going back, total annual precipitation increasing almost everywhere in our climate projections. Summer precipitation decreasing in all of the watersheds. And this is particularly important for an area like ours where we don't get a lot of rain in the summer to begin with. But summer's when we have crops growing, when we have plants growing in the wild, right? When we have a lot of animals using the rivers, summer precipitation matters a lot. And as we go into a warmer world in the future, we're going to have less water coming from snow and ice melting in the summer. And then we're also seeing less precipitation. So this is a little cautionary tale to look at the seasonal details. Perhaps some seasons hold more practical significance than others. In fact, more precipitation in the winter may or may not be helpful depending on how you're thinking about it, right? Getting more when we already have a lot and less when we already don't have enough is not quite what we would really hope for. All right, more charts. I will never let you out of here. We should have called this "Come See Aquila's bar charts." But I just wanted to summarize what we just looked at. Here are the observed trends at our climate stations. Temperature, got mean annual, minimum temperature, maximum temperature. Just looking at those seasonal variations, noticing, a big increase in summer temperature in particular, which is really driven primarily by that minimum temperature increase. Notice how high that bar is for minimum temperature on the upper right. Takeaways from this, though, there's seasonal variability. Mean temperature, mean annual temperature obscures a lot of the details that you might want to think about if you're planning specifically for, say, heating and cooling costs or agricultural impacts. Precipitation, you see is on average, right? We're not showing the variability here, just the average. Decrease in winter precipitation, an observed big increase in spring precipitation, less changes in the other seasons. And then parallel with this, here are the projected changes for the future for 2071 to 2100, as summarized by watersheds. Again, we're seeing the seasonal variability. Big changes in the summer continue, though. Notice now, maximum temperature takes over as having sort of the biggest increase in the summer, whereas in the historical record, we saw minimum temperature had bigger impacts. So there's this kind of change in the details of the trends going forward in the future that is very interesting to look at. And then precipitation here, projected changes, big increase in winter precipitation, small decreases in spring and summer precipitation. Though I haven't normalized this, summer precipitation going down might mean a lot if the summer precipitation to begin with was already very little. So different seasonal patterns for different variables. Another takeaway that I always try to share with my classes is this idea that it's not too late, like it is not time to give up yet. I mentioned how carbon dioxide stays in the atmosphere for a long time. We are still making a decision as a global society about which of these paths on that chart we're going to follow. These are the different SSPs, those different emission scenarios. I taught an intro to climate change class last winter, and I was able to say confidently then, we are not on the SSP 5-8.5, that scary red line at the top anymore. We were following that, it seemed like, early in my academic career, but advances in clean energy technology and electric vehicles and so on meant that we got to shift away from that. Now, we could go back to it, right? We are still choosing, and we are making decisions that you can't come back from quickly, since our carbon dioxide is going to stick around for so long. I'm sorry, this is an ugly chart with just too many decimal places. I should have made a graphic of this, but I just want to compare the numbers here. For mean annual temperature, if we're looking at a different SSP, a different future greenhouse gas concentration amount, we get different projected changes, as you would expect. I was looking at this one over here, the left column, SSP 2-4.5. We see here for Seattle and Vancouver, example cities, a warming of a little over 2 degrees in that scenario. But just, yes. Sorry, I know it's the real numbers. I just added some Fahrenheit for my American friends, but okay. Then as we go across SSP 3-7.0, that number at the end, 7.0, means there's a bigger change to energy imbalance. That's what that's representing. Notice we get a bigger increase in temperature. Sure, makes sense. SSP 5-8.5, here we're up to 4 degrees warming for Seattle. I mean, not necessarily you and me, but a little bit, all of us get to choose which of those we're heading towards. I won't go into all the precipitation details, but they're different with the different scenarios as well. So 2 things this tells us. It's really important that we choose the right trajectory. Also, though, it's really important that we plan for a range of potential futures. If we're making adaptation plans for a local community, that community could do all at once to mitigate its greenhouse gas emissions locally, but it's going to be affected by things that happen around the world. All these big global scale changes in economics and technology are going to influence it. So we need to plan for a wide range of futures because we don't know what the rest of humanity will decide to do, right? So I think it's very important and useful to look across a range of future scenarios. All of these details come down to an argument that geography matters, place matters. We need detailed local data if we're going to make informed adaptation planning decisions, if we're going to advocate for policies that would mitigate or reduce our local greenhouse gas emissions. We need locally relevant data because we saw so much variation in those figures across space, variation among seasons, and these differences in the details of the trends between the observed historical changes and the future projections, right? So we need these details at hand, easy to access for planners and policymakers in particular. We also need local data to help people understand what's changing and care about what's changing locally, right? It's really easy to discount something that seems far away in time or space. And now I will show you my favorite graph I've ever made. This idea, we're here, and where is climate change in time and space, right? And here we go. Often we think of, the polar bears, and I am very sad about the polar bears, but they're far away, right? And we're thinking like, that's something that happens in the future. My kids will worry about it. It's happening in the Arctic. It's not here where I am, right? And to change that perception, I think one useful tool is to look at locally specific data so that we shift that idea of where climate change is in time and space back to something local and relevant. This is my garden in the summer of 2021 when we reached over 100 degrees. We broke all the temperature records for Bellingham. And I had all these little cute seedlings out there and they were just frying in the heat, right? So I was out there pouring water around and I put these umbrellas and things over my plants. That's a sign of climate change literally in my backyard, a memory that I have making it personal. Right now this autumn, I still have sweet peas and nasturtiums blooming in my yard. It's weird. And we didn't get any days below freezing until December. It's unusually late, right? Our average start of frost is in October. So I'm seeing this right now. My bird bath has not frozen over. These local signs, things are changing, and I need to plan for that so I know when to plant my crops and harvest things, right? This local relevancy makes climate change personal and local as well as global and political. So my work is a little drop in that direction, but I encourage you all, if you're concerned about this, to think about framing discussions of climate change in terms of your local community, in terms of things that people care about. Probably the most important thing that we can do to try to address climate change as individuals is just to talk about it with other people that we know. And this is coming out of a lot of scientific kind of climate science, psychology related literature, pointing out that it's something we're worried about right now and that it's affecting things that we actually care about, fishing, gardening, skiing, whatever, helps keep it in people's minds. So when they're going out to vote or they're making decisions about buying that electric vehicle, they're thinking that it's something that's relevant to them. So that's my pitch to you. I am working on this project, ongoing project. I am going to add all sorts of variables over the next year. I received some very generous funding from the Salish Sea Institute, the EPA, and Puget Sound Partnership to work on this project with some graduate research assistants. You don't have to look through this whole list, but I'm just going to add a lot of things. If you have questions about how stream flow has changed or snowpack has changed, come back and ask me in June because I will have the analyses then, right? This is just the first installment in a series. And eventually I'm going to hopefully really soon send the Salish Sea Institute a manuscript summarizing the stuff I talked about today. Hopefully that'll turn into a series. And these results are going to be shared with the International Health of the Salish Sea Ecosystem team that has Canadian and US participants. It's a kind of government agreement, and they're going to incorporate some of this into their indicators of ecosystem health for the Salish Sea region. So there'll be lots of places to look at this and see what I found. Okay, so thank you so much. I have this list of people who have helped me, Natalie Furness and Emily Bradford, who are working on said manuscript with me and helping me think through how to communicate these things. And Jenny Broadhurst, as I said, ongoing, endless support is so wonderful. And Michael with the EPA for this supporting, trying to find funding for this. Huge, huge thanks to the Salish Sea Institute, EPA, Puget Sound Partnership, and the Spatial Institute. None of whose logos I managed to get on this slide, but I put their names in, so I guess. You can explore draft maps, I'll say, of my results if you want to. They are up online in this interactive format. Show it right here, what this looks like. Sorry, I'll bring that back so you can find the URL. Yeah, I know, it's late, okay. Last thing, Ginny knows how I get with the demos. I just want to show you, you can click around and zoom in and out and see all the details for the stations and so on. I will not do a full demo. Okay, now I would be happy to take questions. I think, should we start with an audience question or two and then do an online question? And Ginny's going to help field the online ones? Yeah.
Going back to the really colorful maps, I'm a different kind of scientist, so I don't really know the terminology, but I noticed there's a trend of and this one, the last map here. Yeah, there's a trend of less rain kind of closer to the Salish Sea, and in the other temperature maps there's it's colder or it's warmer near the Salish Sea. Does that have to do with population or closeness to water or elevation? Or
yes. Okay, so this question was about why we see these different spatial patterns in temperature and precipitation, where when we're looking at precipitation values in the past or the future, we see there's this rain shadow, it's called, this dark red area in the center of the Salish Sea. That is caused because we have these mountains on the Olympic Peninsula and on Vancouver Island that block and redirect storm systems. So we get less precipitation on the leeward side, on the opposite side of those mountains. They kind of funnel the storms to other places. That's a consistent pattern that happens in the present day, and it will happen in the future. We might be bringing different amounts of moisture to the area, but we still expect the same effects of topography. Same with temperature. It's colder as you go up in the mountains, and it's warmer as you get to lower elevations closer to the ocean. And so we see that fingerprint of geography in the past and in the future. Yeah. One more from the audience and then an online one.
So kind of curious, we've seen, or at least I perceived, an increase in forest fire activity, especially actually in some of the northern BC watersheds. Are you modeling for that or and controlling for it in your analysis?
Well, I'm not controlling for it, but certainly it would be something to look at, right? You can create these models of oh, sorry. I'm not remembering to repeat the questions. I promised I would. Okay, asking about wildfire, increased wildfire activity. Am I modeling or controlling for that? I'm not thinking about that as something that I need to control for with my analyses, but my analyses indicate that there will be an increase in wildfire activity based on climatic changes alone. We're seeing drier and hotter conditions, which, no big surprise, create more fires. We're also seeing this increase in what's called the fire season, right? There's part of the year where it's too rainy, we don't tend to get fires. We're seeing a longer season that has conditions that could have fires. So it's not just that fuels are more flammable on an individual day, there are more months of the year that could have fires, and that adds up to more acres burned over the whole year. I'll put some of that in the assessment eventually. Wildfire modeling, though, is really tricky because you don't know exactly where an ignition will occur. So you're just kind of talking about the probability of a fire. Yeah. Okay, an online one?
Okay, what's the story about anomalous heat waves in terms of frequency and temperature?
What's the story of anomalous heat waves? Okay, well, as the world gets warmer, we shift the average conditions. So on average, it's warmer. But we also change the distribution of the extreme events that go along with that. I don't have the figure ready here, but I've got a little bell curve if you want to see it. So we just naturally expect to see more extreme heat events. That one's pretty straightforward. Precipitation, interestingly, also sees this shift in the extreme events because a warmer atmosphere can contain and move around more moisture. And so when it does rain, we tend to get heavier rainfall events. It doesn't mean that a warming world makes it rain more often, but when it does rain in many areas, we're seeing more extreme events that would cause more flooding. Okay, any other in-person questions? Yeah.
Some of your maps show conditions back to 19.
Mm-hmm.
Some of them started 19.
Mm-hmm. Well, excellent. Great question. Perhaps I could show these same maps that we're looking at here with the future projections. Oh, did it again? Gosh, it's written in bold and underlined, so you all understand on the instructions to presenters. I'm so sorry. Okay, what's the right baseline to use? I show some analyses that go back to 1901 and some that start in 1991. In my web maps in the bigger report, I actually do show these sorts of maps going back to 1901, so you can compare from that starting point to the future projections. I didn't show that here because I already showed you 5 million maps and charts, right? I think that the right baseline is probably looking back to that historical time period, but it depends on what your goal is. If you're trying to tell people the conditions you're used to right now are going to change, it makes sense to start with the conditions as they are right now. If you're trying to think, well, hey, when we distributed water rights or chose the types of agriculture we do in different regions, a lot of that happened in the early 20th century. So then we might want to look at changes from that historical baseline. If we want to say, here's the cumulative effect of climate change, we probably want to go back as far as we can so that we're including all that historical change that has already occurred. And the reason I don't go back before 1901 is because there just aren't enough climate station records in the past. In other parts of my research, I use paleoclimate methods like dendrochronology. I'm actually wearing tree-ring earrings today to try to reconstruct what climate was like in the past. But when it comes to climate stations, we are pretty limited in this region to not much before 1900.
Maybe this is quick. Why 2071? Why did you wait? What's the significance of waiting?
Why 2071 to 2100? So when we're working with climate data, we typically look at what's called a climate normal. It's a 30-year average so that we can kind of wash out any extreme outlier events to get just a consistent average. So that's why it's a 30-year window, and I'm using a 30-year window in the past. 2071 to 2100 is usually the end date for a lot of our common climate projection data that we get. Beyond 2100, we're just so uncertain about what humans will do, it becomes less and less meaningful. We do look at those projections. Sometimes they are available, certainly for something like sea level rise, where we have already committed to sea level rise that has not happened yet. Even if we just totally stopped emitting greenhouse gases, we would still see sea level rise continuing for centuries. Those sorts of things we model farther into the future. But basically just the uncertainty about human actions, population, and so on becomes too great after 2100. Though any year now, we're going to shift, right? This has been true my whole academic career. So it must be time to start looking the next 30 years. Yeah.
I got to give you the hook.
Okay, come out.
So thank you everyone for your interest in this. Sorry we didn't get to all the questions. There was a lot of questions about policy and local impacts, and I just wanted to offer the Whatcom County Climate Action Plan is a really good resource for information. It's actually a really excellent document. So Google that, Whatcom County Climate Action Plan. Thanks, Aquila, for an awesome talk.
Thank you.
And thanks to Janine and Western Washington University Alumni Association for helping behind the scenes put this on. And we are about to go offline. Thanks.
Okay, thank you, everyone.